Hello everyone, welcome to this video in which we're going to be talking about the order up to model, or more familiarly in the inventory management parlance, it's called the base stock model, right? And the difference between the base stock model and the EOQ model is that the EOQ model has a fixed order quantity, while the base stock model is based on a fixed time period for replenishment. All right. And we'll go over some of the basics of this model, and we'll talk about some key performance metrics. I might not do everything that's there in the textbook, but we will cover a decent amount of it. All right. So let's get going. So as an example, to explain all the concepts through this, let's look at the InSync pacemaker supply chain. So Medtronic's InSync pacemaker supply chain, there is a distribution center in Mounds View, Minnesota. And this particular distribution center supplies 500 different sales territories throughout the country, right? Now, we will look at the decisions that are made at the distribution center itself, and we'll also look at the decision made by one particular salesperson and her territory. We'll consider Susan Magneto and her territory in Madison, Wisconsin. Now, the objective here is, because the gross margins are high, to develop a system to minimize inventory investment while maintaining a very high service level target like 99.9% in stock probability. Now remember, these are pacemakers, and so if a particular patient needs a pacemaker, the demand literally has to be satisfied in a few days, maybe sometimes in a few hours, rather than wait for a long time. So hospitals will not maintain inventories of pacemakers. They will get them from salespeople, and salespeople have to maintain inventories of these pacemakers, right? Now, in the timing and order up to model looks something like this, that all time is divided into periods of equal length. Now this could be an hour, a month, a week, it could be anything, but the same period is continued. So this is almost like a time series model, if you remember, where data was collected at equal intervals of time. Here decisions are made at equal intervals of time. So think of it this way. So you have a store and you're selling some item. At the beginning of every day, you look at how much inventory you have of the item, and then you place an order to replenish. So that's just approximately what this boils down to, right? So now, so during the period, the following sequence of events occur. So you can place a replenishment order, inventory is received, or random demand occurs, right? So if you look at the picture very carefully, I'm just going to enlarge it just a little bit so you can see a little bit more. So so you place an order at the beginning of the period, you receive the order right after you place an order, and then some random demand occurs and you have a certain level of inventory at the end of the period. And then based upon that level of inventory that you have, you place the next order. And then again, you receive the next order, then demand occurs and so on. Now, a few things here. Now, you can have lead times play a huge role in this, because once you place an order, if the lead time is 1, you will receive the order next period, right? If once you place an order, if lead time is 2, this order will arrive right here. So the lead time becomes very important in these fixed time period models. And for the example that we are looking at, we will we'll take a lead time of L equal to 1. So essentially, if a hospital places an order for a pacemaker, they will get it the next day, right? That's basically what's going on right there. All right, so let me change that back again, right? Now, we compared the order up to model to the EOQ model. Let's compare that to the news vendor model. The difference between the news vendor model and the order up to model is that in the news vendor model, you place a single order, right? And inventory becomes obsolete after one period. So you place a single order. If you don't sell it by the end of the season, the inventory is gone. But not in the order up to model. Inventory never goes bad. So once you manufacture these, say, pacemakers, as in the example, the inventory is useful forever. Now again, we talked about, I gave you similar examples before. think of vending machines, right? So vending machines are also replenished at equal intervals of time. So vending machine, let's say there are Pepsis in the vending machine. The Pepsis that go in the vending machine don't go bad for a very, very long time. So you can never say never. Everything that is made consumable or useful is always goes bad. Even pacemakers, they have a product lifetime. So FDA approves them for say 5 years or 10 years or 20 years or something like that. And yeah, so you have to keep that in mind. Now, demand occurs during replenishment. No. So, news vendor, there is no option of replenishment with news vendor, except maybe that model where you saw you can make two orders instead of a single order. But in the order up to level, like the EOQ model, you'll be making many, many, many orders, right? So, news vendor applies to short life cycle products, while the order up to model applies to long life cycle products with uncertain but stable demand, right? That's the idea. So let's compare Susan's thing with the distribution center. So the average monthly demand at the distribution center is 349 units, and this is what it has been. Now, one thing I want you to notice is that demand goes up, then goes down, then goes up, then goes down. So it almost looks like there is a pattern, but there's actually no pattern in this demand. Demand is variable, but there is no pattern. So there's no seasonality in this demand. So that's the thing to keep in mind. The standard deviation of so we can calculate the average value and we can calculate the standard deviation of these numbers. So average and standard deviation, we have the numbers, and that's the yeah. These are the values for the distribution center. Now let's look at Susan's numbers specifically. So as far as Susan is concerned, total annual demand is 75 units. So that's annual demand is 75 units. And so if you convert that into average daily demand, it'll be 75 divided by 260, assuming 5 days a week and 52-week year. Average demand is 0.29 units per day, right? And in this case, a Poisson demand distribution works better for slow moving items. So at the distribution center, you don't consider this a slow moving item because you sell a decent amount of inventory every time. But if you just look at Susan's example, you don't sell that many units in a day. So Poisson demand distribution might work better. Now, even for the distribution center, Poisson demand might work, but maybe we'll see. We'll see how you can evaluate that, right? So, what is the Poisson distribution? Again, we talked about this before, but Poisson distribution is the outcome of a random variable with the Poisson distribution. It is a discrete distribution. That is the distribution the random variable that follows this distribution takes specific values, and the values are positive. So no negative outcomes are allowed, and that is true for most real life counting. Anything that you count, right? So in this case, we are assuming the demand is countable. And that's essentially what you're looking at. Now, a lot of times we assume demand follows a normal distribution, and that's okay, because with normal distribution you can get non-whole number demand. So you can have demand that is say 3.5 or 7.6, 7.856 or something like that. But that's okay, because you can always round it up and down and adjust the probability just a little bit. But here, specifically, the random variable only takes those specific values. Now, the main difference between a Poisson distribution and a normal distribution is that normal distribution needs two parameters, the mean and standard deviation, and they are independent parameters. And you need to know both parameters to know what the distribution looks like, but not so for the Poisson distribution. Poisson distribution is characterized by just a single parameter, which is the average value for the Poisson distribution. That's because the way the math works out, the standard deviation of a Poisson distribution is equal to the square root of the mean. So if the mean is, say, 1, the standard deviation is also 1. If the mean is 4, standard deviation is 2, right? So it's just the square root. Okay, now the Poisson distribution is ideal for when you have slow moving products, right? Products that have an average sale of 20 units of fruit over a particular period of time, whatever period of time you're considering, right? So, for example, if you go back to the distribution center, now so here, see that the monthly demand is 349 units. So if a month is the is the unit that you're looking at, then you would not use Poisson distribution because 349 is a very high number. If you convert this into weeks, right? So if I convert 349 into weeks, that will be 349 divided by 4.33. 4.33 because there are 4.33 weeks in a month. So that will make it 80. Even then, 80 units a week, even that is high. So remember, the rule of thumb is that whatever time period you choose, if the average sales are 20 units or fewer, then you use the Poisson distribution. So that's the basic rule of thumb, right? So slow moving products. And that is true for Susan, right? Her annual demand is 20. So if you convert it into daily demand, it's 0.29. If you convert it into weekly demand, that'll be slightly higher, but still it is not as high. It'll be 17.32, right? So it's less than 20. So even if you do weekly demand, it is less than 20. So you would use a Poisson distribution for when managing Susan's inventory, right? So you can see here the different Poisson distribution. So with the large mean, the Poisson distribution start taking the same sort of bell-shaped curve. So as the mean increases, it becomes closer and closer to the normal distribution. So you might as well use the normal distribution anyway. But with a small mean, the Poisson distribution can take many different shapes. So that's something to keep in mind. All right. So, so this is what the Poisson distribution looks like, and you can generate all of these numbers in Excel, right? We will do that when we do some of the calculations. You don't have to look up tables or anything, but you can generate these numbers in Excel. Right? Okay, so once you have these numbers, so consider so this is the probability function. Because these are discrete values, you can have direct probability function. So this is the probability that 0 demand for that time period is 0. This is the probability that demand is 1. This is the probability that demand is 2, and so on, right? And this is the cumulative probability. So this is the probability. For 0, the probabilities are the same. For 1, the cumulative probability is the sum of the probabilities. For 2, it's a sum. For 2, this is sum of the all three probabilities. Anything 2 or less, right? Cumulative probability. So you'll notice that this adds up to 1. And finally is the loss function. So the loss function is slightly more complicated, but again, you can generate this in Excel. All right. So let's look at some basics of the order up to model. So the order up to model, you have something called on order inventory or pipeline inventory. So those are the units that you've placed an order for, but you have not received yet. You have on-hand inventory, which are a number of units that are physically on your on-hand. Now, why is on-order inventory important? On-order inventory is important because in most order up to models, you do not assume lost sales. So if somebody comes to your store and say, somebody comes to Susan and say, hey, can you give me a pacemaker in a day? She can say, hey, I might not be able to give it to you in a day, but if you wait 2 days, I have on-order inventory that will arrive in 2 days and I can give it to you in 2 days. And that might be okay. I mean, many times these surgeries, you could potentially push them for 24 hours if you're waiting for a particular kind of pacemaker and so on. So you have on-order inventory, you have on-hand inventory, and then of course you have back orders. So back orders are the total amount of demand that is not satisfied, right? So if you're counting inventory, on-hand inventory at any point in time, on-hand inventory will always be positive or 0. You either have some units of inventory on hand or 0, but the inventory level is different from on-hand inventory. So inventory level is the amount you have on hand minus the back order. So if you have no inventory on hand, and you have back ordered 4 units, your inventory level is -4. So inventory level includes any back orders that you have, right? But finally, you have inventory position, which includes on-hand inventory plus on order inventory plus on-hand inventory, right? So it is what you have on hand plus whatever has not reached you yet minus any back orders that you have, right? So that's the inventory position. So these are the 4 big things. So on order inventory, on hand inventory, inventory level, and inventory position. So 5 things, back order. So these are the 5 important definitions that you have to keep track of when you're doing the order up to model. And of course, a big S, this is called the order up to level or the base stock level. So the base stock level is S. And so that's the maximum inventory position that is allowed to you. And also that is the inventory position that you come up to every time period, right? So if in each period the order quantity will be S minus the inventory position. So suppose that the base stock level is 4, right? So you've set a base stock level of 4, which means that you will bring up your inventory position every period to 4. So if the inventory begins at, if the period begins with the inventory of -3, how many units are ordered? Well, if your period begins at -3, you order 7 units because you have to bring your inventory position up to level 4, right? Now, if demand is 10 in period 1, then how many units are ordered at the start of period 2? So that's another question that you can answer very straightforwardly, right? So these are the things that you can. It's very simple, right? So if demand in so if the period begins with inventory position of -3, so because if you remember the usual cadence, you'll notice that you place an order right at the beginning of a period, right? Based upon the inventory that you have right at the beginning of the period. So you're not waiting for any orders to arrive and you're not waiting for any demand to occur. So the order is placed right at the beginning, right? So going back to this particular question that we were talking about. So here, so if a period begins with the inventory position of -3, you're going to order 7 units, right? So you're going to order 7 units and the inventory position goes up to 4. So that's the order quantity. Now, if you start with -3, right, you placed an order for 7. So now your inventory position is 4. Now, if demand in the period is 10, then 4 minus 10, the end of the period, your demand goes up to, so 4 minus 10 will be -6. Then at the beginning of the next period, you will order, well, 6 plus 4, 10 units, right? So because demand is 10, you're basically ordering 10 units. So a period's order quantity is equal to the previous period's demand, right? So that's what it comes down to once your inventory level becomes less than capital S. So whatever base stock level you said, if inventory position becomes less than the base stock level, from that point onwards, it's a pull system. You look at previous period's inventory and you order the exact amount each period, right? So that makes your inventory ordering very straightforward. Okay. Now, but what determines the inventory level? So at any point, how do I know what my inventory level is? So inventory level at the end of any period will be the base stock level minus the demand over the previous L plus 1 periods, right? So L is the lead time. So if lead time is 1, it's the previous 2 periods. If lead time is 4, the previous 5 periods, right? And the reason for that is, what is the inventory level at the end of period 4, for example? So let's say that the base stock level is 6, lead time is 3, and you have 2 units on hand at the start of period 1. So the start of period 1, you had 2 units on hand. What will your inventory level be at the end of period 4? Well, at the start of a period, the inventory level plus on order always equals S, because remember, you're always bringing your inventory position up to capital S. So at the end of every period, your inventory level comes back to capital S all the time, right? So in that case, how do you find the inventory level at any period? Well, you look at the previous the lead time plus 1 number of periods. You look at all the demand that has occurred, because all of those orders, because it takes 4 days for the order to arrive. Once you place an order, you know exactly what order is going to arrive today. So if you look at all the previous demands and you know what order is arriving today, then you can calculate the inventory at the inventory level at the end of a particular period. So it's always going to be the order up to level minus the demand in the previous L plus 1 periods, right? So nothing ordered in periods 2 to 4 will arrive by the end of period 4, right? So none of that is going to arrive. So all demand is satisfied, so there is no loss, and all demand is satisfied, so we'll assume that there's no lost sales. Given that, we can so the logic tells us that the inventory level at the end of this period will be the order up to level minus the demand in each, the last L plus 1 periods. So Why is this important? This is important because this tells us that we are not just going to look at single period demand. So D1, D2, D3, D4, these are single period demands. What we actually need to know are the demand distribution for the previous L plus 1 periods. Once I have that, I'm always going to subtract that from my order up to level to tell me what the inventory position, inventory level is at the end of any period. All right, and that's the idea. Now, there is a lot more to talk about, but this video is all gone on for already 20 minutes, so I'm gonna break this up into a different video. So I will see you all in the next video. All right, take care.